Okay, hello everyone. I'm Emmanuelle Autret. I work at the French Marine Research Institute, Ifremer in France, so as Jeff Pioli. Today I'm gonna present you the work we are doing in the framework of the upcoming TRISHNA mission. It's a collaborative work between Ifremer, Météo France, the Institute for Biodiversity in France, and also, of course, people from CNES working on the TRISHNA mission. So the title is how to design a new coastal 100-meter resolution SST product, and we have called it a Callista product. So as you know, SST at 100-meter resolution can bring a lot for many coastal applications. For example, in aquaculture, by monitoring or defining sites, in marine biodiversity studies, in monitoring water quality, and also, for example, as we could see this week in several presentations, for example, on studies about coral bleaching or marine heat waves. So we are provided with high quality observations of about 1 kilometer resolution. They are continuously improved in terms of SST retrieval, cloud masking, etc. They are available in the user-friendly GRIST format, but it's still challenging to provide good quality data in coastal areas because of the complex shoreline, because of aerosols, because of the difficulty to discriminate between cloud and turbidity, for example. So pixels very close to land are contaminated by land or aerosols in the atmosphere, for example, and are often flagged as bad pixel. And for many applications in coastal zones, 1 kilometer data can be considered as low resolution data. So as we have already heard this week, we can find very high resolution data in existing missions, for example, from the Autret mission and from the Landsat mission. These missions are primarily dedicated to land observations, but they also occur in coastal zones, and there is no dedicated SST products. They are available in multiple files and in several formats also, and in coastal zones and also over inland waters, cloud, land water, and ice masking is not relevant. So, as presented by Bimal and Stefan, the upcoming missions are the CNES ISRO TRISHNA missions, the SPG and the LSTM missions. They will occur in coastal regions. They will have better radiometric performance than Landsat, for example, and they will have higher temporal sampling also. So you can see it was presented by Bimal, but you can find a poster here introducing the TRISHNA mission for high resolution observations in coastal ocean and continental water. So we have decided to propose an experimental product called Callista, providing coastal SSTs from split window algorithms, and it could be compared to the direct test algorithm presented by Emily yesterday. The coefficients can be estimated in our experiment from collocated grist data from also Ertitov. We have assessed also cloud, sea, land, ice mask, and they can be validated against grist 1 kilometer SSTs or in situ measurements, and also from radiometer measurements. And they will be distributed in a grist format. So first, we have chosen a quite small area presented here on the right-hand side panel. And EcoStress and Landsat 9 data have been downloaded and pre-processing. We have tested several nonlinear SST algorithms as the one you can see here, and several ways to estimate the coefficient. And we have also set up the validation in terms of MDB and in terms of collection of in situ measurements. I'm not going into details of the details of this figure, but to summarize, due to bad cloud masking and land masking in the original EcoStress dataset, for example, but also in the Landsat 9 dataset, we have selected for EcoStress, for example, here a limited number of scenes with visual quality controlled, and they have been collocated with grist 1 kilometer product. When we estimate the coefficient from the 1 kilometer product, or when we validate the high resolution data, we apply a smoothing filter to compare the same thing. To summarize the results, the split window algorithm, so the first version of the split window algorithms gives quite good results with biases from 0 to 0.2 or 3 Kelvin, but for sure it can be improved. As the standard deviation is quite large, but it also can be improved for sure. And the major sources of error here comes from the data set we play with because of the presence of outliers and remaining clouds, despite the visual control. If we come back to the land sea temperature that is provided in the original EcoStress L2 product, so this surface product is estimated from the test algorithm, and as already presented, for example, by David Wesse in a paper and in the grist meeting 2 years ago, this product exhibits a large bias of about 1 degree Kelvin. It's the same concerning the Landsat 9 mission. So with the Calista product and the split window algorithm, results are better and can be even largely improved. As I mentioned, in the original product, the clouds, despite a cloud masking method, the clouds are usually not detected. For example, on the left-hand side panel, you can see an EcoStress image, and 3 minutes later, on Sentinel-3 images, and the large cloudy region in the south part of the image with very low temperatures was not detected as a cloud. It's the same for the right-hand side images, for example. The images from EcoStress and also from Landsat are quite noisy, so we are working also on method to improve the image quality and to denoise the radiance fields. So as also mentioned, the land mask or sea ice mask, etc., just geolocation is a problem in the original data set. So we are working also on a method to improve them. So as you can see here, on the top, it's in red. It's a land mask for eco-stress granules. So we have constructed our own mask. So as a conclusion, we can see that the split window algorithms can work well for retrieving SST from these very high resolution observations. We have to improve many things, such as the denoising of the images, and also the SST retrieval algorithms for sure. But I think the critical point is the cloud masking and also land, water, ice dynamic mask. So we are going to work on it in the coming months. And a critical point also is to build an in-situ data collection to be able to validate this kind of product at the coast and for pixels very close to the coast. So it's also a huge task in the coming months. So you have a poster on these topics here too. And as a perspective, the area will be extended at first over the French inland waters with experts in these areas, and also over Pacific French overseas territories for marine retrieve and coral bleaching issues. And I would like to thank CNES for funding and also for very fruitful interactions in the framework of the TRISHNA mission. And I would like to thank also David Wessey from the eco-stress science teams for many discussions on the eco-stress data. And thank you also to the organizer. I'm very happy to meet new faces working on the TRISHNA mission. So thanks.
Thank you, Dr. Autret.